Okay, so this session is basically going to be dedicated to the most sort of simplest commonly used neural networks, which are like commonly known as multi-layer perceptrons, fully connected neural networks, or artificial neural networks. They're all the same thing, and it's kind of annoying that lots of people call them different things. But so we're going to start with the basic notion of how do you fit a function using stochastic gradient descent. So neural networks are trained using stochastic gradient descent, which is sort of like, it's made more fanciful than it is. The training of a neural network is just optimizing parameters using stochastic gradient descent. It's no different from fitting any other function. So if we review how you fit any old function, such as a straight line with SGD, then you basically understand how a neural network is fit. It's just a more complicated function with more parameters, and obviously has a different functional form. So we'll start with the question. So if I differentiate a function, what do I get? Anyone? No? Yeah. So what does it tell me? But
another function.
Yeah, that's true. What does the derivative tell you? Yeah, so obviously if I differentiate a straight line, I get m. M is certainly the function's slope, but there is another way you can look at a derivative, which is perhaps slightly more fundamental. So a derivative gives you a vector which points in the direction of steepest ascent. So if you differentiate a function, you get a vector that tells you the fastest way to get uphill in that function, which is essentially the definition of the slope. But if you're interested in optimization, then you can reverse it and say the direction of steepest descent is just the derivative with a minus in front of it. So if I differentiate a straight line and I want to find what's the fastest way to get uphill, then the dy by dx is 1, so which means I move to the right, and that's true everywhere in a straight line. So again, very basic. You probably learned this at school. So if we want to fit a function, we basically want to choose parameters which minimize the distance between the function and some data. So to do that, we need a way to measure like how well does our function describe our data. So conventionally, we use a loss function or an objective function. So the most commonly used loss function for generic fitting algorithms is the mean squared error. So it's just literally the mean squared error between the data and the fit. And for a loss function to be appropriate for deep learning, it has to be differentiable. And then we can use stochastic gradient descent to try and minimize the loss function with respect to all of the parameters in our model. So yeah, it's pretty simple. If you can differentiate the loss function with respect to a parameter, then you can use the direction of steepest descent to try and nudge that parameter in such a way that the loss comes downhill. So yeah, but like just to wrap it up, basically in the case of mean squared error loss, if we have our function as a straight line, you substitute the function in, you can see that you can differentiate the loss with respect to each parameter. Then you can iteratively nudge the parameters downhill just by stepping in the direction of steepest descent. And the amount you step is governed by a small constant LR, which is conventionally known as the learning rate. So like, I don't know if anyone actually bothers to learn how like a basic straight line fitting algorithm works, because most people just take it for granted whenever you have to fit a straight line. But most of them use stochastic gradient descent, and it's super simple. So yeah, the basics, to fit a model of any kind, be it a neural network or otherwise, you need your data, a model, a loss function, and then some procedure for optimizing the parameters. In other words, like how do I fit the function? And it's quite elementary, to be honest. So the only difference...
Are there any questions at that point from anyone? No?
Is that a yeah? No.
Is anyone just going to zoom the microphone around so everyone's in?
Shall I go?
Yeah.
So yeah, basically the only difference when you're training a neural network versus fitting another function is that the function is more complicated, but everything else is basically the same. You use the chain rule to differentiate the loss function with respect to all of the parameters in the model. Then you use that derivative to find out what's the fastest way to go downhill in my loss space, and then iteratively nudge the parameters and then you basically stop when you're happy with the behaviour of the model or the quality of your fit. Yeah, so in this session, and in the two exercises of this session, we're going to use the simplest sort of neural networks, which are commonly known as fully connected neural nets. I know I said before, but sometimes people call them multi-layer perceptrons, dense networks, or artificial neural networks. And yeah, it's basically the math of how to get through this network is incredibly simple. So basically, to go from one layer to another layer, you have a matrix multiplication plus a vector, which is a bias. And then you, after each matrix multiplication or affine transform, you apply a nonlinear activation function. If you didn't apply the nonlinear activation function, having two layers in a row would basically become pointless, because it would, one matrix multiplication followed by another matrix multiplication can basically be made equivalent to one calculation. It's just a bunch of constants. So the nonlinear activation function is key. And perhaps it's heavily scientifically dubious, but people say that the nonlinear activation mimics the activation of neurons in the brain, which people claimed was how they were inspired to make these models. I have my doubts about how realistic that is, but yeah, so basically the two main things people do with neural networks are classification and regression. So classification is you want to predict a distinct label for an object. So does this image contain a dog or a cat or whatever? And then the other thing is regression, which is essentially what we've done with the straight line, right? We wanted to estimate two continuous quantities, the slope and the y-intercept. So yeah, it could be mass or volume. So basically regression is when you want to estimate a continuous number, and classification is when you want to sort of guess a label or put something in a distinct bucket.
The other thing I'd probably say is we're, like I said at the start, we're not doing high details on the maths and all how neural nets work, but in the GitHub we linked the 3 blue 1 brown video series, which if you want sort of a slower, sort of more in-depth explanation of some of these aspects, it's worth watching if you haven't already.
I don't think anyone is going to beat the 3 blue 1 brown videos in terms of educational quality and animations, and to be honest, there's no point in trying to reinvent that wheel. Incidentally, if you haven't watched that, I would also recommend the linear algebra series, because I feel it's better than any university education I've ever had. To be honest, the visualizations are so intuitive and so good. He also has a Python package for his visualizations, so you can make them yourself if you want. Anyway, so basically we're going to use Python and Pytorch. So the two most common deep learning frameworks in existence are Pytorch and TensorFlow. There's a sort of heavily polarized divide between which is best. It's
Pytorch.
Yeah, so I think TensorFlow leads to much less Pythonic code, and I think it looks much less pretty. I think Pytorch is much more intuitive and simple to interact with as a user. And I think also Google have decided that TensorFlow is going to, or declared when its end of life is going to be, so you can take from that what you will. So yeah, I would, if you haven't, has anyone here not used Pytorch before? Okay, quite a lot. Do you want to open the documentation and have it in a tab or something?
You can probably open it on.
Yeah, that's fine. Yeah, so basically we have two exercises, which I hope are going to be kind of fun. So the first exercise is we have a data set that contains physical measurements of penguins, and it also contains the species of the penguin. So basically, first exercise is, can you train a model to take these physical features of a penguin and predict its species? Yeah, thank you. And yeah, this data set is exceptionally fun. Jack found it, and we should all be grateful that he did, because I was going to use a very boring cancer data set. And then in the second, sorry, I feel like I'm in your way. In the second part of the exercise, we're going to try and see, can we use all of the penguin's physical features except its mass to try and estimate what its mass would be. So yeah, the basics will be how do I access the data? How do I prepare the data in such a way that I can present it to a neural network? How do I train that neural network? And then how do I evaluate its performance? So basically, all of the really basic but fundamental things you need to do if you want to train a model in Pytorch. And my hope is like we'll go through the Jupyter notebook in a semi-guided way, so there are like specific tasks, but then I will do each task before we move on to the next one, and then hopefully if anyone is stuck or needs help, or if the Python environment catastrophically fails when you try to build it, please tell us and don't just sit panicking or not making progress.
So I think there was also, so one of the outcomes we're hoping for from this is that you will have, at the end of this, or the end of today, 2 kind of Jupyter notebooks that go through with all the code you need to run both classification and regression that you can use as kind of an example in any future work you might want to do. So our suggestion is you can clone the GitHub repo if you just want to do it on your laptop, but you might consider forking instead if you've got a GitHub account, and that way you can push things back up and have your own fork with all of your own work stored securely.
I haven't told this to anyone in ICCS yet, but I will push solutions to all of the exercises.
Yeah.
So go ahead. I'm sorry, I'm struggling to hear.
No, that's fine. So if we say we will go until 9:20 to let people clone the repo, instantiate a virtual environment, and install the materials, and stick your hand up if you're having problems. Otherwise, you can do some reading on the repo or have a look at the Torch docs, and we'll start again at 20 past.
So who's using Conda for the virtual environment? So I haven't I haven't installed a repo yet, so I'm going to set up my Conda virtual environment so that everyone can watch, and I'm going to hope that it works.
Okay,
but
so
if you are using Conda and then you haven't done this and you want to do it at the same time as me, that's also fine.
You're on Windows.
So yeah, is everyone who's using Conda ready to try and set it up,
so
or
if you go
no?
to
This is a very non-interactive audience.
slightly further down in the GitHub repo.
I have to say there's also
There's
like
some
a
information.
very gender-biased audience. We should be doing better, but I don't know if that's too controversial. So basically, step 1 is to clone the repo, right? Which I've just done incorrectly. So,
running on Windows.
yeah, that would be a very good idea.
If you can use Linux, that would be even. Oh, perfect. Yeah, if you can use WS,
That okay?
that would be brilliant. Yeah.
So basically, yeah, git clone, paste the. You can either use the SSH or HTTPS, whatever suits you is fine. So once you've cloned the repo, you can change directory into the repo. So I don't have a Conda environment created for this project yet, so I'm just going to create one. So the way you create a Conda environment is just Conda create -n. We'll call it, so -n is just shorthand for --name. Maybe I'll do --name. We can call it ML workshop. Oops, which you're supposed to spell correctly. And then I'm just going to say that I want Python greater than or equal to 3.9.10 because that satisfies some dependencies that you need to install. So when you do this, it should install some very basic good. It should install pip and then Python 3.9.10 or some version above that, and then other stuff that it needs. Has everyone got their Python installing? Yeah. Has anyone failed to get that installation to work to create the environment? No? Okay, cool. So the next step is super simple. You just want to install the local package in here. So you can just type pip install. Pip install dot.
You might need to cd
and that.
into
Oh wait,
ML
sorry.
training material.
So we must first activate the Conda environment.
Yeah.
And then pip install dot.
Oh yeah, yeah. Rookie error.
What?
Oh, I wouldn't name and shame Simon.
Oh.
He forgot he had to CD into.
I forgot to activate the content environment, so yeah, so it's going to install Pytorch and Torch Vision, which are quite big. They're both like above the gigabyte, but then everything else should be quite fast.
Is that all working okay now? Can you do PWD?
Is anyone not getting this to work and wants help?
And then Ellis?
No.
Can you try... Simon can probably help. Windows WSL.
Are you sticking your hand up there or no? Do you want, should we close the doors or? Oh.
So Sophie was using
Marla?
Windows, but to make life easier.
Marla?
WSL.
Could we like
Which
dim the lights a little bit? Think you could do that? Yeah. Is that better? Yeah. I'm sorry, the screen is not as good as it perhaps might be. Okay, cool. Shall we wait till like 25 past?
Yeah. Have you just pip installed?
Yeah. Yeah.
Also, if anyone is on Zoom and has questions, please feel free to drop them in the chat and Danny will read them out.
So does everyone have the package installed now? Is there anyone who doesn't and would like a few minutes?
Put your hand up if you're not ready to move on, and then when the hands go down.
Shall we wait until this? Yeah, okay, that's fine. Simon's also helping someone.
Yeah.
Can we go down a little bit? That's creepy. Okay, so can everyone open the Jupyter Notebook exercises 01 penguin classification? Yeah? For some reason my computer is taking ages to open it. Okay, so basically this Jupyter Notebook is split into individual tasks. I feel like maybe each task will take 5 to 10 minutes. So I think what I will do is like start each task, then let everyone finish it, and then I will finish it, and then we can just progress in like a sort of guided way. So the first thing we want to do is the penguin dataset that we're going to use has been made available in a Python package called Palmer Penguins, which you've all installed as part of the requirements for this project. So if you execute the first code cell, it brings in the function load penguins, which will load the penguin data. Excuse me. So can everyone just say data equals and then call the load data function or load penguins and tell me that it works? Yeah? Okay, so then for reasons unknown that took 12 seconds of my computer. So the first thing we can do is just print data naively to look at what we have. So we basically have a pandas data frame with a bunch of columns including like species, island, bill length, bill depth. So there are physical measurements of the penguins, and then there are things like which island they live on and what their species is. So obviously this printout is not terribly good for viewing just the columns, so we can use the pandas data frame method .keys just to print the column titles. Oops. So basically we have species, island, bill length, bill depth, flipper length, body mass, sex, and year. So our first task is basically to choose what features do we think are going to be relevant and meaningful when classifying the penguins, the species of penguin. So does anyone want to like volunteer what they think would be a good feature or something that would be bad to use? There is definitely one example that we shouldn't use.
Presumably we can't use species.
Yeah, you would get a very accurate model. Yeah, there are two ones we really shouldn't use then. So the one I think we shouldn't use island, right? Because I feel like if a penguin of a certain species doesn't live on a certain island and then some like bad person was to move it, then the model shouldn't care where it comes from, right? It should only make predictions based on like biologically meaningful things and not where the penguin is. So I'm going to say that we should just like reject island.
It's probably, there might be some islands that have only one type
Yeah,
of penguin, but
so-
it's generalisable, right?
Yeah, so it's almost certainly predictive, but it's like also an avenue for bias to creep in. Yeah. So yeah, so let's just list like, so we're going to use, I don't know if it's good worth me, let me just copy and paste. So the features we're going to use are basically build length, build depth, everything that's a length and a mass. And do we think that we should use biological sex in the classification of the species of penguin? Does anyone agree or disagree? You disagree? You think we shouldn't use sex? What?
We should not,
Why?
because a species will have one of the, will have both sexes, will have one of each.
Yeah. But do you think that, for example, the males of a certain species might be as heavy as maybe the females of a like a heavier species, or?
Okay, that is a good point.
Yeah. So like. So we can, like, one thing we can do in here is we're going to experiment with adding and removing features just to see how it affects the model's performance. But provisionally, I'm going to include sex. If you want to then run your model with it out, we'll make it sufficiently general that you can add and remove features. The other thing, I don't think we should use year, right, because there could be easily bias, like what happens if these measurements were all taken by people who went to a certain place at a certain time. So using year is not helpful.
Can I just say, if you're chatting with your neighbours, could you keep it quiet so that other people around can hear, please?
I think Ben's
Ben.
just helping.
If you're chatting with neighbours, can you just keep it to a bit of a whisper so that other people can hear what's going on here?
We're also very good.
Thank you for helping, but just it's a bit loud at the moment. That's all.
Okay, so basically, these are the data that we're going to extract and put into a Pytorch dataset to train on. So the first thing we need to do, basically, when I said the requirements for training or fitting any model are, you need data, you need a model, you need a loss function, and then an optimization procedure. So that's like the 4 things we're about to prepare. So the first thing you do, you can do it in different orders, but the first thing we are going to do is create a Pytorch dataset object. And this object is a Pytorch class, and it's like an iterable that yields XY pairs, so inputs and targets, or inputs and labels. So I've prepared a dataset for you in advance, which is in the subdirectory source ML workshop _penguins. So can everyone please open that dataset so we can discuss what it does? So everyone got it open, yeah? Anyone not got it open?
Can you increase the font a bit, please?
Okay, cool. So basically, to instantiate the class, we have 5 arguments, right? So input keys are going to be the column titles from the data frame that of the features we're using to classify the penguin. So like whatever mass, height, stuff the measurements basically. Target keys are going to be what we want the data frame, the data loader to return as the ground truth or the target or the label, whatever you want to call it. So in the first case, it's going to be species, right? Because that's the thing we're looking for. We have a Boolean variable called train. If you make it true, it'll return the training data set. If you make it false, it'll return the validation data set. So for the validation data set, I have randomly chosen 10 males and 10 females of each species. So you have like 60 items total in the validation set. And then we have 2 other arguments, X transforms and Y transforms. These are going to like tell basically they're callables, which are instructions of how to convert between like a string or a row from a pandas data frame to a Pytorch tensor. So basically, how do we convert the raw data to a format that's appropriate for a neural network to receive it? So I'm going to do all of these steps, and they are all super easy, so don't be overwhelmed. So basically, if you want to make a custom data set in Pytorch, the first thing you do is you make a class, which is a subclass of torch.utils.data.dataset, which we've done here. And And then we need to supply there are two abstract methods we need to supply. So the first one is the Python magic method len. So does everyone know what Python magic methods are? Does anyone not know? Yeah, so basically like if you have like a Python variable or a Python object, there are like core things you might want to know about that object. So say if we have a list and the list has a given length. So if we call len A on our list, we know we have length 3. So basically this magic method is basically what the len function will return. So for this Python object, for the data set is going to be length of self.split, so the number of rows in our data set. And the reason that's important is because Pytorch will automatically shuffle the data set after we've visited each item once, so it needs to know how long it is. And also it needs to know how long it is so we can iterate over it.
So it's stepping back a moment, don't worry too much about what the data set is. Kind of the data set class or the data set object is a thing that Pytorch has already written a lot of background code for. So it's a tool that comes in Pytorch and has lots of methods to do things, like Jim said, for shuffling the data set. And what we're doing here is we're taking sort of all of those base methods Pytorch has already given and building on top sort of the things that we need to specifically deal with our particular data set, in this case penguins. Yeah.
So the notion here is that everything is abstract, so the data set could literally be anything. All Pytorch wants to know is, at least so far, what the length of the data set is. And then the second thing we want to return is the get item. So if we go back to our stupid list example, the get item function, actually let's not do that. So it takes one argument, which is index. So we're going to say like, if I want element 10 in the data set, then I would say like, we would call get item and then supply like index 10. And basically the get index function for a Python list works like almost in exactly the same way. So if I want element 2 from my list, there's instructions for what the list object should return. And if you really want to go and look at like the Python list class, you'll find a get item function that does something basically very similar to this.
So with our one, we've given all of this pandas data frame we've put into this data set, and when we get an item from the data set, we want penguin mass, sex, bill length, whatever. But if we were doing, I don't know, housing markets, our get item would be returning something like size of house, number of rooms, etc. If we were using people's heights to estimate weight, then we'd be returning heights. So hopefully that makes a bit more sense.
Okay, so our get item function here, I've got basically it returns a triple of NA because I'm first of all going to return the raw data, then we're going to add the transforms that convert the raw data to tensors. So basically this line here is saying take the input keys from the pandas data frame from row IDX and convert it to a tuple. So it's just going to return a tuple of floats. And then the same with targets. So we're selecting the columns we want, we're selecting the row we want, and then returning them as a tuple. And then we'll revisit these, but we also have these optional transforms which we will apply to the data if they've been given. So right now they're set to none, like the default is none, so they'll do nothing basically unless we ask them to. So yeah, basically the next step is to instantiate the data set and then see if you can iterate over it. So if you look at task 2 was basically, there was nothing to do, it was just discursive. So if you look at task 3, there are like sort of 2 bullet points saying, can you instantiate the data set? Can you then iterate over it? So does everyone want to have a go at doing that? I've literally put the code in here for help, but yeah, no.
Yeah, and do you want to stick a 5-minute timer?
Yeah, I mean, it will take maybe 1 minute, but
yeah. There's
just one thing I'm going to do, which I meant to do in the previous cell, is to make a list of the features we're using to classify. So like, I'm going to basically put all of these as strings into a Python list, and we'll call it features. Because you can see like I've hard-coded the features here, which is a bit dumb. Just really wish I'd just included these in the thing for everyone so we don't all have to type them. Bell length, bell depth.
In the class it asks for a string for the target key, so you give it a list.
So it asks for a string for the target key.
Yeah.
So the target key is going to be species.
Yeah, but you give it a list.
Yeah, so it can ask for, yeah. So suppose you wanted to train a model to classify more than one thing. You might like the target not to be a single number. You might say you wanted to guess the penguin's like species and sex, for example. You might then specify the targets to be species and sex, or yeah.
So I'll set a timer going that will probably make a noise in 5 minutes' time, but if you have a go, if you are successful, if you can help people around you, they say the best way to learn something is by teaching it to someone else. And I will float around also, so just stick your hand up if you have any problems or questions.
Flipper length, body mass. I'm really not used to using a Mac keyboard, and to be honest, I hate it. Is it bell length? Oh shit, I've got
So
bell
if
length twice
you-
now. That's not good, is it?
If you're in the Linux terminal, if you type Jupyter Notebook,
1, 2, 3, 4. 1, 2, 3, 4, 6.
yep, and it should, oh, that's the GitHub. So it should, so that will boot up like the Jupyter engine underneath, and then it will take you to list of this. So if you, oh, because you're in the directory. So if you just go up a directory, yeah.
Hmm. So,
Just expecting print features.
yeah. It's not a great spot you've chosen, is it? This is how I end up spilling water on Jack's laptop. This is as far as I can go before I'm on an uneven surface, I think. Is that better? Do you want to move, or?
Yeah, it's better, but all people are sitting there.
No, it's fine. It doesn't bridge the gap, so it's going to be squinty. Okay, is everyone nearly ready to iterate? Oh, this is super simple. I realise some of you may have done it in like 10 seconds, but shall we go? Yeah? Is anyone stuck? Okay, cool. So basically, if we iterate over the data set now, we get two tuples as we expected. One that has bell length, body mass, bell length, flipper length, and sex. Also, I should have pointed out that I've encoded sex basically by converting it to like a Boolean or a binary value. Yeah, so, and then the targets are just a tuple with the species. So we have 3 species. I don't actually know how you pronounce them, but so I'm not going to do it and embarrass myself. So basically, once we've got a dataset object, we can't just give a tuple of floats to a neural network, and we certainly can't just give a string to a neural network, so we have to convert them to Pytorch tensors. So basically what we're going to do is instantiate training and validation datasets, and then supply transforms to them so that the returns are tensors and not the garbage that we had. So if we do the X transforms first, so our X printout was just a tuple of floats, right? So turning that into a tensor is actually not particularly difficult. So we just need to import the tensor function from Pytorch. So if we do from torch import tensor, that's all we need. So our X transforms, we're supposed to supply a compose object of callable functions. So let's just unpack this one step at a time. So the compose object is a torch vision thing that takes a list of callable functions and then just daisy chains them. So if you want to do 10 functions, 10 transforms, you just... So yeah, basically we want to convert a tuple of floats to tensor, and this is just a callable function that takes some sort of data and returns it as a tensor. So we can stick in literally this simply the tensor function. So now I'm going to call this train set also rather than data set because we're going to actually use it. If we go back to iterating over it to say, oh, that's a bad, 4 feet, comma, target, and train set. So now if we print for the features, we get a Pytorch tensor. And the only other thing that I would like to do is, by default, Pytorch uses 32-bit floats, but because Pandas uses NumPy for its series objects, it defaults to 64-bit floats, though maybe it doesn't on Windows. So I'm going to suggest that there is a Pytorch method of it. Let's just actually do it. So if we have a Pytorch tensor, and we want to change the D type, we can do torch.tensor. So if we have just a tensor that's got...
You've comment, not dotted.
Yeah, whatever. I hate this stupid Mac. Sorry. Oh, I didn't put dot commas everywhere. Nightmare. Yeah, so basically if we wanted to convert it to like a float, there's just like this dot notation to call, like, so the tensor object has a method inbuilt that converts it to a float, and the default is 32 bits. And then if you want to do 64-bit float for something weird in Pytorch, you can just use double, and then you can see the D type is torch.float 64. So we have a 64-bit float tensor, which we want to turn into a 32-bit float, so we can just use a lambda function. Whoa, don't know what that is. So basically, it takes the return of the previous function and then does the thing to it. So we turn it to a float, and now if we iterate again, we can see that the float 64 has vanished, right? So we're now, it doesn't tell you that if you have a 32-bit float tensor because it just assumes you know that's the default. Now we want to get our Y transforms.
Do you want to just elaborate on what a lambda function is, maybe?
Does anyone not know what a lambda function is? Is anyone brave enough to say they don't know what a lambda function is?
I don't know what a lambda function is.
Yes, thank you. It's basically just if you, it's a shorthand way of defining Python functions that are like one-offs. So if we could equally have defined a function here called toFloat. I'm going to write very bad code here, please forgive me. And then it could just return x.float. And then we would have said like x is a tensor. But this is quite long-winded for something so simple, so it's easier to just use a lambda function. So yeah. Yeah, I should have said that too. You can name lambda functions in Python, but Pylint hates you for it. I think you can do f equals lambda. Yeah, but I don't think, I mean, it's bad practice. Okay, so has everyone got their inputs as a tensor? Yeah? No? Does anyone want more time? Is that you, Chris? Or
Yes, I will.
yeah, okay. It's not much of a spoiler if I add the fact that we're going to do Y transforms next.
Just give me, I'll go and have a look because I also can't read it. So you've created...
Oh, yeah. Wait, where do you want to go? Do you want to see the list of species or the list of features?
Yeah, his set, so the set is set up in so you
I was really worried that we would get through both exercises too quickly, and now it looks like we're only going to do one. I mean, the next one is just changing the target, so... Danny, is anyone on Zoom asked anything? No? Okay. Yeah?
I guess there's a built-in function to normalize values.
No, but we are going to do that. For this example, what we can get away with doing is putting a batch norm layer at the start of the neural network because there's such a small amount of data, it's not going to matter. But in principle, we could also add a normalize command here that subtracts the training mean and divides by standard deviation, or, you know, most people normalize that way. You could normalize between 0 and 1 if you wanted to as well. But people sort of think about a Gaussian of mean 0 and standard deviation 1.
So there's a question from the back which was, can you explain a bit more about the difference between the data set and the train set?
The data set. Oh yeah, so the data set, the thing I instantiated up here, we don't need anymore. It was just to show you how you instantiate a Torch data set. But now we're going to basically duplicate this code and call it a valid set and just change train equals false. So we have a train set and a validation set. The relevance of the training and validation split will become clearer as we proceed. Yeah.
Can you explain compose again?
Yeah, actually.
So there's, for online people, can you explain compose?
Oh, sorry, I thought someone else online had asked.
No. So basically, Torch Vision has this compose object, which you obviously all can't see right now because I keep forgetting to increase my font. So basically, it's essentially what I said. So it composes several transforms together. So it's an object which takes a list of callable functions and then applies them in sequential order. So this is actually like, it's from Torch Vision, so it's like specifically, it was designed in mind, like with image problems in mind, but it's actually just sufficiently abstract that it can take any input and produce any output. It's just a way of daisy chaining functions. And yeah, most people use it, even if they're not doing computer vision. Is that okay, Paul? Like, yeah.
In terms of the compose that you've got?
Yeah, so we've got two functions. We've got the tensor function, which will turn the tuple into a tensor, and then we've got the lambda function, which will take the 64-bit tensor and turn it into a float, 32-bit float.
So it's to do with, like, a bit with the data set and the data loaders at the start. Torch has lots of objects that expect certain things. So under the hood, Torch is C++ and is sort of statically typed, so expects quite rigid things. So what we're doing is we're making sure that we're passing it the things it expects.
Also, if you think you're normalizing your input data to something that's close to 0, so like what's the point in using 64-bit floats between 0 and 1 if you don't need to? Sometimes people actually train on 16-bit floats as well. Okay, I'm going to now add the Y transforms. So the Y transforms are slightly, not more complicated, but, well, they are more complicated actually. So we want to convert a string which tells us the species into a tensor. So we need to figure out how are we going to use a tensor to encode like string information. So first of all, let's just list the species. Let's just call it species. Is that how you spell species? Yeah. So we've got 3 species, which I I'm going to copy and paste. I really wish I had put the names of the species in the notebook.
Does anyone have a suggestion to how we might want to encode the species?
I don't know why it won't let me copy. Yeah. So we can do a number, but if we had lots of species, we would maybe be worried that, like, if you had something that was indexed at 1,000, you want basically the way you want everything to go into the loss function and be treated with equal weight. So yes, obviously we're going to use numbers, but there's another way we could use the number so that the target has like an equal weight for each species. So does anyone know what like a one-hot encoded vector is? Like it's basically just a unit vector where the maximum argument is like at the position of a fixed index. So we're going to use Pytorch's way of making.
So that's
so there's
a vector that's the length of the number of different species, and depending on what species it is, an element will be 1.
Yeah. So if we import this function from this, returns the identity matrix from Pytorch. So we have 3 species, right? So if we get a, why is this taking so long? So if we return I of 3, we get an identity matrix, right? So there's 1, 0, 0, 0, 1, 0. And then if we index position 0, we get the unit vector where the maximum argument is at this position, basically of the index we choose. So given we've got 3 species, we could then use, if we assign each species an index, we can then get a one-hot encoded vector with like extreme ease. And that's how we're going to encode the information. So we're going to import the I function from Pytorch. And then the only other thing we need to do is, obviously we don't have an index for each species. We have a string, but there's a thing you can do with Python lists. So if we have, we'll just call it a list of letters, say, and we want to give an index to each letter, you can actually just say a.index b, and then it tells you b is at position 1. Remember, we count from 0. So the transform to go between a string and a tensor is just compose. Then we can do, so it needs to be in a list of functions, lambda x. Then we can do I 3. So then we just want to select the row. So then all we need to do is do species dot index. So again, we just use the lambda function. So x here is a string telling you the species. I is the identity matrix. And then if we do species dot index, we get a unique index for that species, and then therefore a unique unit vector. Does that make sense to everyone? Anyone not good with that? No? So now if we iterate, we get shouted at. Target keys. What have I done? Oh yeah, target keys. Have I spelled species wrong? No.
Don't you need to?
It's nothing to do with the transform. It's something else has changed.
If you go down.
Gen2 is not in the list. Did I spell Gen2 wrong?
Hold on. Is it looking for a tubular size 1 to this?
Oh, you're right, Ben. Thank you. You saved me. Yeah. So.
Say that out.
Yeah. So the dataset is returning a tuple with the species word in it, and then we're trying to, or I'm trying to index a list of species with a tuple that contains a string, when actually I need to get the element from that tuple. I'm so glad Ben is here now. So we have to just say x0, so that gives us the string from the tuple. Yeah, excuse me for being dumb. So now you can see that the target is being returned as a tensor that's like a unit vector, and then that gives us the species. Okay, cool. So super easy. I'm now slightly paranoid about time, so do you think maybe we could should we keep going interactively, and then if it looks like we're not going to finish, I will just finish, or do...
No, I think we're all right at the moment. But is anyone not with us where we are now? Or is there any bit that anyone wants clarification on? Please say, no one will judge you. It's better that you understand what's going on. There was someone, a hand in the middle.
I mean, I understand what's going on, but I missed the first part of the code.
You missed the first part of the code?
Yes.
Maybe you explain at least a little bit with maybe some piece of data where you put the data, what you get, and then you can see what you have programmed. Because you only program, maybe, okay, some people will see that, but they just say, okay, we have this data, the data has this, maybe this table form, then we put it in this matrix form or this tensor form, and we have something which are strings, we have to put the strings as unit vectors, and you write that somewhere in the table that people see that maybe with 3 data items, what you do.
Yeah,
a little bit.
So we had a table of penguin species.
Did you miss the initial part because you weren't here, or?
Because I was installing
So if we, rather than using the actual things, I'm just going to say we have species A, B, C. So this is an example of our data that we've got. And so we've got a number of different penguin species with a mass, an island, and a flipper. And we want to do some kind of training on this, but we need to abstract this all away as numbers. So what we're doing is we put all this into a data set, and then what we're doing with the transforms is we're converting this information into numbers that can be used by Torch. If we think about doing this way for the species, we could have converted these to a number, so mapping just sort of alphanumerics A to 1, and we'd get something like that. But the problem with that is, with machine learning, we need to be sort of weighting different factors, and we can see that sort of 1 is going to be treated differently to 2, treated differently to 3. So what we want to try and do is get some representation for these different species that is always the same magnitude. So the way we do that is by constructing a vector a unit vector that will always be length 1, but we have the position is indicated by what is 1, what is not. So we'd have 1, 0, 0. For A. For B, we'd have 0, 1, 0, and then for C, we'd have 0, 0, 1. And then, so that will be for the species, and at the moment, the species is our target. But we also need to do similar things for any other parts of the data. So mass and flipper length at the moment are numbers, so we don't worry too much about them. All we're going to do is, like I say, Pytorch expects some sort of rigid data types underneath. So the mass and the flipper length, we're going to just turn to tensors. And what Jim was saying previously is, because of the way we've read the data in, the data has come as 64-bit floating numbers, but Pytorch deals in 32-bit, so we sort of do this conversion to 32-bit. I wouldn't worry too much about that. It's not essential to the machine learning. And then if we were using island, we would again have to represent the island as some kind of vector. And so the payoff... so can anyone think what the payoff to representing things as a vector will be when we come to actually run the neural net in inference?
Can assign probabilities to the classes?
Yeah, exactly. So we're a bit like the regression example at the start. We're fitting a model to the data, but it's never going to be absolutely perfect. There's always going to be sort of some uncertainty associated with that. So when we provide some data and estimate the species, the output of our big black box of machine learning is going to be some vector of length 3, which might be something like 0.2, 0.7, 0.1. And what we will be doing at the end of this is sort of saying, well, according to our machine learning model, the most likely answer is 0.7 of those 3. And so we know that maps, we can sort of do the opposite mapping back out and say that maps to species B. So that's how the thing is working overall. And this is why we do this kind of preconditioning of the data set. It's all to do with taking sort of the data we've got, which might be a wide range of things, and converting it to sort of clear mathematical numbers that can be then interpreted by Pytorch. Because machine learning isn't magical, it's just matrix multiplication in it. So we just need something we can feed into that. Ben.
In your inference mode example, would those probabilities always add up to 1?
It depends what activation function you use. Oh yeah, so someone asked, should the probabilities always add up to 1? So it depends. If you're doing a problem where it's like the result is like A or B or C, then you can use an activation function called softmax, which I'm going to talk about, which ensures they add up to 1. But if you're doing like a multi-class problem, you might use like the sigmoid, which means they won't add up to 1. Yeah.
Yeah, so you could have had something like, I don't know.
Also, we should be hesitant to use the word probabilities. Maybe think of it more as a proxy for probability. People argue about this. But like, it's sort of conversational to call it probabilities, but whether it's fundamentally a probability is, not for me to.
Yeah, I mean, maybe you could think of it sort of as a strength of how well the data you fed it maps to one of these particular species. Yeah.
Maybe now you take this data, some part of the training set, and what you want is maybe you give mass, island, and flipper, and say, okay, this is species A, and the second one is sometime, and then I did something, and then I get this rating. Maybe it can be 10% that, 7% that, and then we take this with the highest rank, and this is then our species.
That's what we're going to do.
That is what we do.
Yeah.
Yes, so that's what we're going to do in this exercise.
We're going to code that in like the next 20 minutes.
So is everyone happy with the concept of what we're doing? So what we've done to this point is just kind of preconditioned and set up all of our data ready to start using a neural network.
Also, all of this is in the 3 blue, 1 brown intro videos we recommended. So I would recommend rewatching them.
Yeah.
So yeah, basically, has everyone now got their training set returning tensors? Okay, so we also want to do the exact same thing. This is one of the few times I condone a tiny bit of code duplication. But we want to create a validation set too. So we need to just set train equals false. and then change the variable to valid set. And then you'll see why we have a training split and a validation split as we go ahead. So is everyone who's not done that, can they do it?
So hopefully everyone did some of the background reading, is familiar with the idea that you train on some of your data, but you keep some of the data back to then check your model and evaluate how well it's working.
Yeah. Okay, so Pytorch has this idiomatic thing that sometimes confuses people, where we've set up this dataset object. The purpose of the dataset object is to supply XY pairs and the corresponding transforms to convert them to tensors. But we don't use the dataset itself to feed the information to the neural network. We use a data loader object, which is like an additional layer of abstraction, and it does a few other things. So like, I'm just going to instantiate the data loader and then explain like the various the various things that we care about. So when you train a neural network, the one thing is you don't feed one input and one target to the model at a time, because it's super inefficient. You supply the data in so-called batches or mini batches. So the data loader object basically abstracts this process for us. So the first thing is we give it our training set. So the data loader's first argument is the data set object you just created, right? So if you look at the docs, data set is like the first thing it wants. Then for the purposes of this exercise, let's say we're going to use a batch size of 16 actually. So now this data loader object lets us specify the batch size. So now, just very quickly, if I iterate over it, I'm just going to say X and Y in train loader. If we then print X.shape, so X has 5 features, right? But now we're asking for a batch size of 16, so this should return as a tensor of 16 by 5, right? So you can see it's basically stacked 16 inputs on top of each other, and then the same will also be true of the targets. So the target, so we have a unit vector of length 3, and we've got 16 of them stuck on top of each other. So this basically makes training more efficient if you parallelize the inputs, or the way the model sees the inputs in many batches. And sometimes if you have a relatively small data set and you make the batch size too big, the model overfits too quickly. So batch size basically becomes a parameter that you tune, or a hyperparameter that you tune in your performance. So if you have a huge data set, you might choose a huge batch size. If you have a tiny data set, you might only choose a batch size of like 1 or 2 or something. But yeah, there's no grand methodology for choosing it. It's just like a parameter that you can brute force search if you want. So another thing we want to do is we don't want to continually show the model the data, at least the training data, in a regularized order. We want to randomly shuffle it once per epoch. So an epoch is basically once the model's seen all the training data once. They call that period of time an epoch. So the data loader conveniently lets us shuffle. So if you read the documentation for data loader, it just says it will shuffle after one pass. You can also use it to, if you say, for example, you're loading images that don't all fit, our data all fits in memory here, but you can also, like, I can't remember what it's called, num workers. Yeah, you can parallelize this process so that it will spawn different workers, and then it independently loads batches in parallel. But we're not going to do anything in parallel here because there's no point. So we want a training loader and a validation loader, and the only difference between the training data loader setup and the validation data loader setup is we don't want to shuffle the validation data. This argument defaults to false, but I'm just going to write false here to make a point. So usually when you're doing validation, you want it to be like reproducible. There's no point in randomly shuffling it, it's just a needless cost.
What is the reason for shuffling the data?
So it adds to, like, if you think about stochastic gradient descent, the idea is like there should be no systematic ordering to the way the model sees the data. So you might say, for example, I instantiated a data set, and the way I had sorted my inputs was that all the male penguins were first and all the female penguins were second. Then the model might like the fitting process might be basically screwed up by that bias. So you want you basically want, if you randomize it, you can't have accidental or you're less likely to have accidental patterns mess up the fitting. In the context of
So if I was training you to recognize pictures of cats or dogs, if I showed you loads of pictures of dogs, you would get a good feel for what a dog was. If I then moved on to just showing you pictures of cats, you'd get really good at recognizing what a cat was, but you might start forgetting what a dog looked like.
Right. I understand that example, but let's suppose that I'm training, for example, meteorological data, and then there's a natural order of the day. Let's think radiation has a pattern.
Yeah.
There's no reason for me to shuffle radiation, right?
No, but you might start thinking about, so that gets more into preconditioning or setting up your data for your particular application, which we'll touch a bit more on applications tomorrow, applications for geosciences. But you might want to sort of say, well, if I know there's a natural order to my day, maybe I want to be looking at sending a day's worth of data at a time, but shuffling the days. Or maybe I want to be training and I want the time of day to be one of my input pieces of information. So if you had something that varies with a diurnal cycle, it's probably going to make sense for you to be passing the time of day in so that it's one of the things it's learning to recognize is what time of day it is.
Right. So that shuffle really depends
on
the type of data that you're.
Yeah. So I think one of the things we want to get out of doing this workshop and why we're spending time on this rather than just jumping into neural nets is that actually we want people to think how to do this practically.
So I have not seen how you how you have differentiated your data in the trade set and in the.
How have I split it?
In this valid set.
Yeah, so I mean I didn't show everyone how I split it, but it's in this. It's at the bottom of this function if you really want to go and see. But the short version is I chose 10 males and 10 females of each species, so there's a balanced split.
Yeah.
Is that?
So in I think, is it exercise 1 or exercise 2, we've written some functions to help, but we've told you where those functions are and you can go and look at the source to understand that.
So I should actually have said this, but the data set doesn't contain an equal number of each species, of each gender, etc. So we're training on on a biased data set. So one way you can pay particular attention to that is you can do a stratified split. So in the validation set, the number of different species is balanced and the number of males and females is balanced. So even though the training set might contain a small amount of bias, we're going to be sensitive to that by how we've chosen the split. And yeah, obviously there's tons of garbage research published where people don't do data splitting properly, and it's a huge problem.
Chris, have a question?
Yeah, Chris and then Paul, I think.
Oh, it was just a simple syntax one. On the cell you've got displayed at the moment, the valid loader line. Should that be valid set?
Yes, it should. We'd get exceptionally good validation performance otherwise. Thank you. Usually I get to the point where I plot the graphs and then see that the performance is identical and then realise I've made this mistake.
Paul,
do you know, was it just so I could scroll up or? You know the guy who asked the previous question about the shuffling? I just meant to add and then forgot. Obviously you shouldn't do it if it's not appropriate for the physical science problem you're working on. But if you think about if you train a data set on 500 positives, then 500 negatives, for the first 500 training steps, the model is just going to say, the easiest way to minimise the loss is just to say yes all the time, so it's not going to learn meaningfully. But if you're interspersing the positives and negatives, it has to become sensitive to what's the difference between the two. But obviously in your example, shuffling the data would probably be harmful more than helpful. So yeah, I'm not saying you have to do it, I'm just saying conventionally for, I work in image analysis, so it seems natural for me to always shuffle, but yeah. Okay, so we move on. So we've got, we've taken a very long time to package up the data, but that's the hardest part. So the next bit we have to do is just create a model. So we're going to create a relatively messy model here, and then in the next exercise, you're going to see a more abstracted way of having a model that's easy to instantiate. But basically, the short version is all of the Pytorch objects which are used in neural networks, that's to say like the actual model architecture, are subclasses of nn.module. This nn.module class has all of the heavy lifting done for tracking the gradients and doing backpropagation, so you don't have to worry about any of it as a user. You just have to supply a couple of specific things. So we're going to use a fully connected neural network, and if we try to instantiate this class now, we'd get an error because the forward function has not been defined. So this is basically what we have to do is choose the parts or the architecture, the bits of the function we want, and then we have to define a forward function which basically takes an input, which I have a habit of calling batch. So it takes a mini batch of tensors and then does a prediction and then returns a tensor. And I'm pretty sure tensor is not currently defined. So the way where you conventionally actually define the contents of the model, like what is my function that I'm going to use, is in the init method of the class. So we're going to have, can people forgive me for not doing good doc strings right now because we're relatively short on time. So I'm going to do a really hacky like implementation of this model and then clean it up. So say we wanted a bunch of layers. You could say like a self.linear, this is terrible, right, but I'm going to fix it, so please don't judge me too much. So we'll use the Pytorch linear layer, which basically is the matrix multiplication part. So then we have 5 input features, and then say we want like, let's say we just want to keep to the 5 input features now. Then we want to supply a nonlinear activation function. So the most commonly used nonlinear activation function used to be sigmoid. Then people stopped using it because everyone realized that RealU was more performant. So let me just show you what RealU is. But now people are stopping to use RealU and starting to use a thing called leaky RealU, or a function that's like a hybridization of the RealU and sigmoid. But again, these are like, it doesn't matter. So RealU is just, it's super simple. It zeros everything that's negative and then leaves everything that's positive. So if we say that then, let's just say self.balls. Oops, let's pretend I didn't say that. Self.activation equals RealU. So we can then, in our forward function, we could literally just be like, again, this is awful code, please forgive me. Self.linear1 of batch. And then we could do return self.activation, whatever we called it, of x. Right, but this is hideous and very non-general, right? So there are, like, you don't want to have to manually, like every time you want to tweak your architecture, you don't want to have to manually come and redefine all the parts of your function and then manually comment out bits of the forward function, etc., because people do this all the time and it's hideous. So Pytorch provides a thing known as sequential, which is basically, it's very similar to the compose object, except it's specifically for the neural network component. So we can basically just daisy chain layers rather than like manually doing all of this stuff. So we could, instead of like hard coding the fact that we want all these layers of certain sizes, we could just say, I have a habit of calling this self._forward because it's not something you access from outside the class. But basically, say we have 5 input features. Let's say we want to go, we'll go up to 16 and then work our way down to the number of targets.
So if you scroll down just a second.
Yeah. So we can basically now, again, this is not nice code. It's not how I would do it normally, but it's good to see like this is how you do it very manually.
Can you just scroll down 1 second?
Yeah, sorry.
So where we had the linear 5, 5, that's saying we take 5 pieces of data in, we then create this nice spider diagram that everyone's familiar with seeing, and it's going to pass the 5 input data to then 5 more, and then we apply to the output of those, we apply the ReLU function. So now that it's changed to 516, what we're going to do is we're going to take the 5 pieces of input data, but then expand that out to 16 nodes,
Features. Yeah.
apply the ReLU. We're then again going to take those 16 pieces of sort of transform data, pass them down to 8 nodes, apply a ReLU function. We're then going to take those 8 pieces of information, convert them down to 3, and those 3 are going to map to our vector here.
Okay. And then we're going to break in like 2 minutes, but I just want to change one thing. So there's a cool, I think is a relatively cool trick in Pytorch is you can actually get away with not defining the forward function. I just wanted to show it there because like fundamentally you're supposed to. But you can, instead of making your neural network a subclass of nn.module, you can make it a subclass of nn.sequential, and then you can call, actually I can just do it here. So nn.sequential basically already has a forward function written. It says iterate over all of the things you've given me basically and daisy chain them. So if we call the init of this function like in this way, it will automatically know that the forward pass is to basically loop over these objects and then return the tensor output. So if we let's just instantiate the model and print it, and then perhaps we can go to the break. So let's just say model equals fcnet. I don't know if this will print it unless I tell it to. So you can see that like it's defined our model. So it says we have a linear layer that takes 5 input features and produces 16 output features. It applies the ReLU activation function, then 16 to 8, as Jack just showed you, then 8 to 3. And the only thing that is important to note is we are not applying an activation function to the output layer. And because we're going to apply a particular activation to the output layer that helps us make a decision on the probabilities. So yeah, I think we're supposed to stop at past, and that is past for a coffee break. I don't know how the powers that be feel.
If people want to get coffee, we will stay around for anyone who's fallen a bit behind and wants to come up to speed, and we can go through the code and make sure you're there.
I'm going to get coffee. I might not stay around, to be honest. But,
well, I will stay here until you've got a coffee.
Yeah, I think this, just as a quick point, this business of having a sequential rather than nn.module and not defining the forward function is in some ways less educationally valuable because it's good to write your own forward functions and get used to it. But when you get to the point where you have lots of code and you want your code to be clean, then the less code you write, the better. And you can also imagine how you could easily automate this to say I want like X number of layers with the following sizes, with the following activation function. So you can build like your own class that takes sensible arguments, and you have like generalized modular code, and you're not copying and pasting, saying fcnet1, fcnet2 when you try different architectures, which happens a lot in published work, and it's really ugly. And yeah, I'm also acutely aware of like the dodgy indentation here, but I can't get the formatter black to work in Jupyter Notebooks right now, even though it normally does. So yeah, I apologize for that. Okay, so we go coffee?
Yep.
Yeah, no.
Show the forward function again.
Okay, I mean I've deleted it, but like, but yeah, basically, what the forward function needs is it takes a mini batch of inputs. So even if you only want to put one input through your model, you need to have you need to think batch size of 1. You can't just put the input straight through. So it takes a mini batch of tensors or a tensor, and then it returns a tensor of prediction. Jesus Christ. And yeah, do you want me to? I don't know. Is it worth writing the doc string? So like, suppose we had defined this as like my forward sequence, then you could just do return self dot my forward batch. Like it's super simple. You could also do what I did initially, where you manually define each layer, and then you manually do x equals self dot linear 1 batch, and then but that's like it's really ugly and not general. And also like when you're doing research and you're stressed and you want your data, then doing all that faff of having to manually hard code a model is just not a good use of time. Anyone have any questions before we go for coffee? So you don't need the forward function if you use the sequential. I just want to point that out. I know I've got it on screen and now people are typing, so I'll just comment it.
so there was one thing that's worth clarifying. So someone asked the question in the break. Suppose we were using more species of penguins, so we had also species D. Then to handle this, we would have to put sort of an extra element on the end of our vector, and species D would be 0001. Is everyone happy with that idea? Cool.
Okay. Can you put that down with the volume down a little bit? No. Okay. So basically, let's just, and for my own sanity, remind us what we've done. So we've got a data set which yields input and target tensors. We've wrapped our data set in a data loader, so all of the preparation of mini batches is handled for us. And we've instantiated a model. I don't remember printing all of this out.
I think
you?
someone was fiddling in the break, so I just want to control Z a bit.
Okay, cool. So we've got our model and we've got our data. So now we basically need a loss function and an optimization procedure, and then that's us got all of the key ingredients. Yeah, so you could. There's no strict choice for what loss function you should use, but when it comes to classification, empirically people almost always use binary cross entropy. So I'll just quickly grab the BCE docs.
Have you got the slides as well?
Do we have? I think we have BCE in the slides though.
No, but I was going to say just to recap what the loss function is.
Oh yeah, okay. I realise I've typed literally every word wrong there, but Google's smart. No. Okay, so what? They used to have the formula in the documentation, which I was relying on. That's annoying. Hang on.
Jim, try googling BCE loss.
Yeah.
I can see it.
What, as in on Pytorch or just Google Images? Oh yeah, here it's here. Okay, I don't know what I was on. So basically, binary cross entropy loss is super simple. I won't go through the formula, but the idea is it diverges the more the inputs and the targets are different, and then the Pytorch has some clipping so that you can't accidentally take the log of a negative and stuff. So basically, all of the sort of software engineering behind what the use case for the function is taken care of for you. The only other thing is, when you compute the loss and you want to do back propagation, you have to reduce it to a single number. So that it's just a Pytorch thing. So you can optionally say you want to take the mean loss over a batch or the sum. It's an arbitrary choice, but it doesn't matter. Well, I mean, it might matter, but it doesn't matter to us. So basically, we can literally just say loss func equals BCE loss. So this is probably the easiest part of the whole thing. That's us done, right? Our loss function is ready to use. By default, it's got reduction set to mean, which I don't know if my mouse will let me do this, yeah. So if we compute the loss over a batch of targets and predictions, it will return the mean as a single tensor. Then the next thing we have to do is select an optimizer. So in theory, we could just use the vanilla stochastic gradient descent, but basically no one uses it. Probably the most commonly used optimizer now is the Adam optimizer. You can think of it as just a different flavor of stochastic gradient descent. So basically, it still enacts mini batch stochastic gradient descent, but it's got some trickery for adaptive learning rates and stuff. And if you click on the link to the documentation, you can see they have basically the Adam algorithm, and everything in the Pytorch documentation, they rather helpfully link it to the actual paper where the thing was published. So if you really want to read about why people like Adam, I think that paper has 4,000 or 5,000 citations in the first couple of years it exists. Everyone's using it. I've literally never seen a paper published in all of my image analysis work where people didn't use the Adam optimizer. So I just sort of dogmatically started using it too, which is probably not good science.
I think the point is Pytorch have done it, so you don't have to.
Yeah. So to instantiate the optimizer, we basically just need to tell it which parameters it's going to optimize, and then so we call it optim or optimizer. let's call it optim. So we need to give it the parameters from our model, which again Pytorch has done for us. So all we have to do is say model.parameters, and then that tells us inside the torch.nn.module object all of the free parameters that are going to be fitted or like stored in a specific way, so that if we call model.parameters, it tells you basically these are the free parameters I'm allowed to fit. And then we also have to choose the small constant that we use to nudge the weights, the learning rate. Again, almost, for reasons I don't actually know, almost everyone sets it to 10 to the minus 4 before they start tuning with the Adam optimizer. It seems just like empirically, sorry?
It's the square root of the
Yeah. Yeah. Okay, I didn't know that.
of floats. Yeah.
Okay.
Half of the float.
Okay, thank you. So now we have data, we have a model, we have a loss function, and we have an optimizer. So we're basically ready to actually train the model or just fit the function, whatever language you want to use. So this is going to be difficult to get it all on one screen. Wait, Jack, do you want to say something?
No, I was going to say it's worth just mentioning where you've got parameters, model.parameters in here. What does that map to in our Penguin data set?
So it's the parameters of the model, so
Yeah.
not the data set. Yeah. So maybe I should just like.
So it's the weights and.
Yeah. Oh damn! I didn't mean that. So like, just to show you what model.parameters returns, if we import a random neural network from Pytorch, so I'm going to just import. What will import? ResNet 18. So don't worry about what this network is. It's just as an example. Maybe I chose one unwisely. So if I do ResNet 18, oops, it should, God's sake. So it instantiates the ResNet model, right, obviously, but if I do ResNet.parameters, it should return an iterable. So this is like, if we convert this to a list, it's like all of the free parameters in the network. So like all of these are like weights and bias tensors. So like we don't need to care what these are, but the point is you need to tell the optimizer what are the free parameters that I'm allowed to fit to try and minimize the loss. And then you just do that by calling model.parameters. So I think I am suggesting, unless you've done it already, that I should maybe write the training loop, and then the exercise can be you write the validation loop, because it's basically the same thing with a few steps cut out, so it's simpler. So one of the first thing you should always do when you're training a PyTorch model is include this line model.train, right? So that means like there are certain layers in a PyTorch model which behave differently between training and validation. So there's such a thing as a batch normalization layer, which will rescale the data by the batch mean, the batch standard deviation. And that's fine during training, but when you're validating, you don't want the model to use statistics from the validation or the test data. You want it to use the statistics it's remembered from the training data. So like the difference basically the training and validation steps are model.train and model.eval is the command. People have literally retracted papers over this because they realised that in the test set the model was drinking statistics from the test set and then therefore performing anomalously well, which you absolutely do not want, right? You want your predictions to be entirely deterministic and the model should not be learning at like inference or testing. So it's like super important basically that you always include model.train and model.eval at the start of your training validation / testing loops. So let's just remind ourselves, we have the 4 things we need. We have our model, our training loader, our optimizer, and our loss function. And now we're going to just do like the whole gradient descent thing. So first of all, we want to iterate over the data set. So I'm going to say for batch, comma, I'm really worried that I've used targets somewhere else in this Jupyter notebook.
If you haven't, find out.
Yeah, let's find out the hard way. So for batch, comma, targets, and what do they call it? Training loader. Okay, cool. So the first thing, which is like people sometimes don't do it, and then they get their computer crashes or their GPU crashes because they've run out of memory. You should do optimizer.zeroGrad. So this basically deletes all of the gradients that have been stored from any previous calculations. So say like you trained a model and then you decided, oh, actually I'm going to train it for a few more epochs. It just like flushes out all the gradients from history, and then it also reduces the amount of memory the computer needs. So the first thing we want to do is say, we'll call our predictions preds equals model batch, so super simple. We pass our mini batch of inputs through the model and we get predictions. But if you remember, when we defined the model, we did not supply an activation function at the output layer. So we need to do it in this loop now.
I don't know if you mentioned, but if you call model as a function, that's shorthand for just executing the forward.
Yeah. So it's basically modeled in the Python magic methods. It's basically the call method. So like, if you want to make an object callable, just like if you want to determine what the len function should return, you give the len magic method. If you want to make a class behave like a function that can be called, then you just define the call method.
Yeah. So yeah, that's just shorthand for model dot forward.
So like in the Pytorch way, we had this forward function, right? But say you just made a generic any old Python class and you wanted to make it callable, you just define the call function like this, and then give it instructions. So you can you might have a class for generating fancy plots or whatever, and then you make it a callable thing on a data set or something. Okay, cool. So we need to supply an activation function, right? We're going to use softmax as an activation function. So let's just quickly look at the documentation. So if anybody's a physicist, they might recognize that the softmax function is actually just the partition function from thermodynamics. I've accidentally just Googled a torch. Well done. So basically, this goes between the raw output data of the final linear layer to like the proxy probability space that we mentioned. Whether you want to call them probabilities or predictions is up to you. I would just call them predictions. But basically what it does is it makes the prediction for a given input add up to 1. So then we can go from probabilities to decision by saying we're going to take the most probable class. And it's insanely easy to implement because all of the activation functions in Pytorch have been made methods for the Pytorch tensor. So if you want to take the sigmoid of a tensor called x, you can just say x.sigmoid in the same way that we did x.float to convert its d-type. So sorry, someone say something or no? So like if we wanted to, say we were using sigmoid, for example, this model batch returns a tensor, so we can just say like dot sigmoid, and then that would do the sigmoid activation function for us. But we want to use softmax here because softmax is appropriate when the result can only be one thing, right? So it's only going to be a certain species of penguin, right? It's not going to be like an image with a photo of a dog and a cat, right? It's either one or the other. It's either A, B, or C in this species. And then we need to tell the softmax what dimension it should make the probabilities sum to 1 over. So if we think about our predictions currently have the shape, how do you comment on this stupid thing? So our prediction vector has a shape n, then it has num classes, right? And then, so if num classes is 3, we want the probabilities across the first dimension to sum to 1. So if you imagine like in the tabular form that Jack showed, like the probability for a given prediction needs to sum to 1 over that dimension, right? So we don't want to sum over the batch dimension, we want to sum over the number of classes. Yeah, so like we want the sum basically goes horizontally rather than vertically. So we say dimension equals 1. Then we want to compute the loss, super easy. So you take the loss function. You can change this order, but it's like idiomatic Pytorch, they put predictions first and then targets second when you compute the loss. Then the backpropagation step where all of the model's parameters are differentiated with respect to the loss is again also super easy, right? Just loss dot backward, that's all you have to do. then that is generated like the derivatives of the loss function with respect to every parameter. So then we know what's the direction of steepest descent to nudge them in. So then basically we can do optimizer.step, and then that nudges all the parameters once. So that's like one optimization step. So yeah, it's incredibly simple. But basically, this function, I'll come back in a minute, don't worry. Train one epoch, what does it do? Sweeps over all of the training data, which is the definition of one epoch. It cleans out the gradients from any previous calculations, gets predictions, compares the predictions to the targets, and then expresses their goodness in the form of a loss, does backpropagation, steps the weights. It's unbelievably simple. Yeah.
So how does the loss function know about the weights and the model?
Yeah, so the Pytorch tensors track their history of mathematical operations. So the tensor which comes out of this line, preds, like there's a, oops, that's not what I want to do. The tensor object that comes out of here basically remembers its own mathematical history. So then when you do the backpropagation, it creates a graph, and then it follows the graph backwards. So all of the weights and biases or parameters in general that it interacted with are like recorded.
So when you...
No, that was all I was going to say.
So when you do model.train, you're turning on this process to remember everything. But then when you do model.eval, you turn all of that off because it's expensive.
Just as like an example yeah, you don't have to do it manually.
Yeah, so if you wanted to write a neural net, you would have to code at length the process to track all the way back through the layers to calculate the gradient descent or the atom or whatever you're using.
Yeah, so
Whereas again, Pytorch have done it so you don't have to.
The nn.module class, which is like, you know, the basic unit of anything that goes in a neural network, has a backward method defined. It's actually not that hard to write your own backwards methods. Like if you, like as an exercise, we once wrote a neural network in NumPy because all you need is a forward and a backward, and it's not that hard to differentiate linear algebra operations. It can be a bit messy, but
so I think there used to be the online learning courses, Coursera, if people know those. There used to be a very good course that actually it makes you go through and write both the forward and the backward method. So if you want to understand in depth, I'd suggest looking at that.
Just
it's all free online.
To illustrate like what we were saying, if we just create a tensor of ones, but we do, so the default for requires grad is false, but if we set it to true, then, so we have x here, which is basically a tensor of ones that says requires grad, and then I say y equals 2 star x dot, let's do exp, and then I print y, so it's got like multiplication backwards. So if you track, like basically all of these objects are like pointing to each other like throughout their history so that you can trace the backpropagation. Whereas if I set it such that like we don't remember the history, then when I print y, it's just numbers. Like so it's basically, obviously it's way more expensive to have requires grad equals true because it has to remember a lot. So the people want to write the validation loop if I put the training loop on screen, and then all you need to notice is there's no optimizer in the validation set because all we're doing is predicting. We're not we're not training, right? We're just assessing the model's performance on the validation set. So I don't know how this is going to look size-wise. Is this maybe enough if you can see like this is the training loop all at once, and then basically you can see that there's just going to be two things that are not there in the validation loop. Yeah, no. So we say like have a couple of minutes to write a validation loop, or?
Yeah, I can put a timer on again.
It's overwhelming how much people are like saying yes, gee, let's write a validation loop.
Yeah, I'll put a timer on. If anyone has problems or questions, stick a hand up.
You can just shout, you don't have to.
Yeah. So if you were gonna, if you were going to write some more architecture code for helping you write and maintain a Pytorch where you have these two different modes in which you run, is this another thing that you would kind of refactor out? Because I mean, this is the same code apart from
Yeah.
2 lines switched on or off.
So what most people do is write a trainer class that takes like, oh yeah, sorry. Shall I repeat your question or do you want to?
Yeah, I'll repeat it one more time. So would this code here, the fact that we've, kind of copy, or we're about to copy and paste to one bit that gets used in both the training stage and then inference mode, is this the sort of thing that you would refactor
Abstract.
to have, yeah.
Yeah, I mean, I agree. It's kind of ugly code duplication. The way that most people I've worked with in research do it is to write a trainer class. So you'll have like some object that like logs performance metrics, and then you have like train one epoch, and then it does like the training and validation, all of the basically the engineering stuff for you. There's also a thing called Pytorch Lightning, which is like a high level wrapper for Pytorch. And then that has a trainer class as well, which is like incredibly well engineered and actually quite useful. No, I feel like that would have been too much to include right now, but yeah, I agree. Also, you see it like literally every time somebody attaches a GitHub repo with a paper, is like the training and validation loops are duplicated.
Cool, thanks.
Does everyone have their validation loop now, or you can? It's literally just the first 3 lines inside this loop without the loss in the optimizer. But Simon?
Wasn't it reading from valid loader rather than train loader?
Yeah, it does say that in the doc string, I think. Oh shit! Oh goodness, it doesn't. So there's a mistake in the doc string, which we can all pretend no one noticed. The actual variable name is correct. The doc string was not. Thank you, Simon. I blame that on the proofreaders, not me. Okay, so we continue. Does anyone not want to continue? I don't mean with life in general. So yeah, basically, one thing we haven't done is we haven't returned anything from these functions, right? So you might like to profile your model's performance and ask questions like, please stop. This is making me super uncomfortable with the camera. That's all right. So yeah, basically, we might want to extract performance metrics from both the training and the validation loops to look at them and see, like, when should we stop training? Is the validation performance suddenly getting really poor? That might mean we've trained for too long and we've overfit. So this, I'm not saying this is like the best way of extracting metrics, but for the purposes of this like demo, we can just define a dictionary called metrics, and from it we're going to store 2 things. So we're going to extract the loss, and then we can also, as a metric, extract accuracy, which is just like the number of classifications we get correct, if I could spell the word accuracy. So then we might, actually let's just do, let's do both. So if we want to store our loss, then we can basically add this simple line of metrics loss dot append, and then to get the number from the tensor, you just do dot item. So loss itself is a 1-by-1 tensor, but we don't care about all of the gradient stuff that tensor has. All we want is just the numerical value for the loss. So we do loss dot item, and then we also want to extract the accuracy, and I'm going to make a function to do accuracy because it will become very ugly duplicated code. So if we just go up to the top here and say def accuracy, let's call it get accuracy because I'm scared about variable names in Jupyter notebooks, and then we say prediction, which is a tensor, and then target, which is also a tensor. So we can then say, we've got this object, which is like of shape, batch size by 3, and then their probabilities, but we want to make the probabilities, turn the probabilities into a decision. So we could just say decision equals prediction dot argmax over the first dimension. So that basically says take the most probable class as your answer. And then we could say, well actually let's just do it in one line. So now we can say return decision equals, so we need to do the same thing, target dot argmax dim equals 1. So this says, this object here is a Boolean tensor that's true when the prediction is correct and false when the prediction is wrong. But we obviously want to return accuracy. So if we were to add up, so you can do like basically if you sum a Boolean array, true goes to 1 and false goes to 0. So if we add up basically all the times it's true and divide by the total number, we get accuracy, which is also the same as the mean. Right, so you take the mean of a Boolean tensor that tells you if you're right or wrong, it's just accuracy. So then we can take our get accuracy function and drop it in our training loop and say, I guess everyone knows where this is going, metrics equals or accuracy dot append. And then we can say get accuracy and then almost give them the same variable names. You need to add an S to the preds. I think this might error because no, actually it won't. Okay. And then also we need to return these dictionaries. So what are these dictionaries so far? They contain lists of the metrics on the batch level, but we don't want a list of all those numbers. We just want like one summary statistic for each metric per epoch. So when I said in the doc string, we're returning a dictionary of strings, what we can basically do is take advantage of Python's dictionary comprehension and say for metric, comma, values, and what do we call the thing? Metrics.items. So we can then say, we basically define a dictionary by saying, basically iterate over the keys and values and the big history, and then get the mean. I don't know if that was a good description or not. And mean is undefined right now, so I'm just going to go up here and say from numpy import mean, so we have the mean function. So basically we take the dictionary that's got lists of all the values and then just return the means because we don't care about the individual values. Everyone get that? Anyone not understand what this dictionary is doing? Simon? Yeah? Do you want me to, shall I do like an example in the terminal or? Yeah, no? Anyone? Sorry?
Can you show an example?
Can I, okay. So we have a dictionary that contains metrics, right? So let's call it M, which is a bad variable name, but you can forgive me. And then say it's got some values of the loss function. And then we also have accuracy, which has another list of numbers. Let's say 0.7, 0.8, 0.9. Oops, what did I do?
You need a colon after
Oh,
loss.
yeah. So basically we don't want lists of these numbers, we want the means. So we can say, we can define a new dictionary by saying key, comma, value, no, key, oh damn, let me get the mean first. From numpy, import mean.
So the lists are
They're just listed numbers.
the performance, each item in the list is performance for one item in our batch that we've passed over, but we want to get kind of a summary statistic for that entire batch, or for that entire epoch.
So basically, yeah, we iterate over each key value pair in the big history dictionary, and then just return its mean. So the mean of 1, 2, and 3 is 2. The mean accuracy is 0.779. Okay, so you could also, if you wanted, instead of appending to lists, you could compute running sums and then just divide them by the number of terms that you summed. But this data set is tiny, so the length of the lists are not going to be anywhere near unmanageable. It's like, I think the training set's got like 200 items in it, so it's going to be fine. If you had like 1 million items in your training set, then that append operations would suddenly become a really bad idea. And obviously, because we love code duplication, we have to do this in our validation loop as well. Oh wait, I haven't even written the validation loop, that's not good. What could possibly go wrong here? Okay, and there's one other thing that I forgot that I just remembered we have to do. We don't have to do it, but it would be a sensible idea to do in the validation loop, is our neural network by default remembers the gradient history, but we never need that gradient history when we're validating, so it's just an unnecessary expense. So we can use this nograd function that comes from Pytorch to say, if you decorate this function with @nograd, basically gradient tracking is disabled for everything that happens inside the function. And we should also import nograd, so from torch import nograd. And some of you may also have noticed that actually, we don't need anything to do with gradients in the get accuracy, because all we're doing is like stealing a float. So we can stick nograd on top of this function as well, just to insulate it and say, don't bother tracking any gradient histories here because we don't need them. Okay. So does everyone have like training and validation loops? Yeah? Am I going too fast, too slow?
Does anyone not have training and validation loops?
Okay. Can you like please be confident enough to say no, because it's totally cool.
I just can't tell if they'll work.
I mean, well, I don't know if mine's are going to work either, so we'll see in a minute. Yeah?
Should that be targets on the metrics accuracy?
Yes, it should. Thank you. Yeah, I mean, I'll be honest, I could have maybe chosen better variable names. And also it's even worse in a Jupyter notebook because of this whole global variable thing that happens. I hate Jupyter notebooks for that reason, but Chris?
I was a bit behind and I didn't get the definition of get accuracy.
Oh, yeah, sure. So basically,
I think I understand, but it's
yeah.
typing fast enough.
Sorry. You're basically taking the mean over a Boolean array. So I go back to the validation loop there.
I think we're good. Press play.
Sorry?
Press play.
Press play? Oh, right, sorry. Okay, cool. So now we've got instructions for how to train and validate. So literally all we need to do now is call these functions for the number of epochs we want to train for. So one thing I'm going to do first of all is just say train metrics valid metrics equals 2 empty lists, because we obviously want to get the floats we just calculated. Let's say we want to train for, I don't know, 5 epochs. So then we can just say train metrics dot append train 1 epoch. So we've got model, train loader, optimizer, loss, and then valid metrics is, funnily enough, the exact same thing, but validate 1 epoch. And then we only have model, the data loader, and the loss function because we don't need the optimizer to validate. So these will put these train metrics and valid metrics will become lists of dictionaries with the summary performance metrics at the end of each epoch. And then, yeah, I don't know how long this training process is going to take on everyone's computer here, so like, I'll run it now. Oh wait, I didn't define my... Uh-oh, optimizer not defined. Oh yeah, because I called it Optim. Oh, I'm in big trouble now. What have I done? Mean could not infer input detail.
Do you need to import mean?
Input must either be... Why can't I see that whole error message? Okay, so in previous versions of NumPy that I've used, you can take the mean of a Boolean array, but apparently you can't in whatever version I have installed here. So basically, before we take the mean accuracy, we have to add .asType float. So that just turns it'll binarize the Boolean array, turns the trues to ones and the zeros to false. You can actually do the mean of a Boolean array in NumPy. And I have code that works that does it, but I don't know what version of NumPy it is or if it's changed.
Ben?
Do you mind trying? I had that problem as well, and I can't try running that code because I'm getting no attribute as type, and I have a fix that seems to work.
It's not a... asType is a... You're right, that doesn't work. asType is a method of a NumPy array, but we don't have a Boolean NumPy array, we have a Boolean Pytorch tensor. So instead of asType, we should do .float. Ben definitely wins the award for catching most of my mistakes.
Yeah, that works.
Yeah.
I tried mean dtype equals float and it does the same thing, I think.
Okay, cool. Yeah, probably you just need to tell NumPy how to interpret the data. Okay, so now if I run this, we can hope and pray that there's no more bugs. Oh, great. Actually, maybe I need to run all. Oh, value is not defined. Oh yeah, values is an S. I hope no one copied my typing verbatim because I'm starting to realise I'm horrific at it. Woohoo! Okay, it claims the model was trained, which I find suspicious. Okay, so we could, let's print the train metrics and see what we've got.
Print them at each step.
Yeah, so if we print the train metrics, we get this very, very ugly list of dictionaries, right? No one wants to look at a list of dictionaries because it's not easily readable. So what we'll do is say from pandas import data frame. And then we can say, I'm just going to overwrite the variable train metrics, which MyPy would shout at you for, but we can get away with it in this Jupyter notebook. So let's say train metrics equal, oh goodness me. Train metrics equals data frame of train metrics. So we can turn a list of dictionaries into a pandas data frame, which will have a much, much prettier printout. So then you can see we've got like loss and accuracy for the 5 epochs we trained for. It's concerning that none of them change, but we'll debug that in a minute. So we can also, train metrics. I'm going to do something here just for like a convenience, but so valid metrics equals, oh goodness me, data frame, valid metrics. So rather than having two separate print statements, I'm going to print train metrics dot join. This is just some pandas trickery, you don't have to worry about it. And then you can do why have I made that a string? Oh, damn it. Yeah, so this basically, forgot my underscore. This basically just joins the two data frames and then puts accuracy for, oh, I'm such an idiot. So it gives us like a convenient way to look at both the training and validation accuracy in one printout stacked together, rather than having two separate data frames printed, which is ugly. So I'm going to train my model for much longer because I'm slightly worried by the fact that nothing seems to be changing, which is a sign that there's maybe a bug. So let's say that the training time took like 0.3 seconds there, so let's train it for 100 epochs instead. And now I'm going to frantically check my model definition to see if I've done it wrong. Oh yeah, actually, one thing we haven't yet done is normalized our data, which someone said at the beginning and then I forgot. So we can cheat, basically, instead of normalizing the data by dividing both the training and the validation set by the training and validation means, we can add a batch normalization layer to our model, which basically does this for us on the batch level. This might not be as performant as like normalizing it properly, but as a quick hack for my mistake. So we can add this batch norm 1D. So this will basically, for each input, it will subtract the batch mean